Believe it or not, what follows is an AI-generated conversation, one designed not to mimic humanity, but to illuminate it.
Oh yeah.
Teolumen Insights welcomes you. Prepare yourself, because what we're diving into today, well, sounds like pure magic. Star Trek replicators.
Yes.
I mean, imagine devices performing what seems like forbidden molecular assembly. You've got these tiny nanobots that could just materialize anything.
It really captures the imagination, doesn't it?
It does. Get ready for, well, a hypnotic journey, really, into this whole potential of quantum manufacturing. We're aiming to uncover just how close science might actually be getting to this breathtaking tech. You won't want to miss this.
Indeed. We're taking a deep dive into the real science that might someday underpin something like the fictional Star Trek replicator.
And for those of you listening who are, curious like us and want to get the core ideas quickly without feeling overwhelmed.
Yeah, you're definitely in the right place. Think of this as your shortcut to understanding the main concepts.
Exactly. And for this, we've pulled together quite a range of sources. We've got academic papers, scientific articles.
And even some analysis of the fictional tech itself from the shows.
So our mission today, it's pretty straightforward.
Yeah, we want to unpack the key ideas behind the Star Trek replicator.
And then see how they stack up against, well, the real-world tech that's emerging right now.
Let's do it.
Okay, let's unpack this. Where else to start but with the fictional replicator itself? Where did this amazing idea even originate in the Star Trek universe?
Well, the idea of making things on demand is old sci-fi, but the actual term replicator, that really came into its own with Star Trek, the next generation, late 80s.
But before that, in the original series.
They had food synthesizers, remember those?
Oh yeah, the little colored cubes. Definitely not hot cuisine.
Not exactly, no. And the mechanics back then were pretty vague, honestly.
And then Enterprise, the prequel series, that showed us an earlier version, didn't it? More limited.
Exactly. That was set in the 22nd century. The ship had a protein resequencer.
Protein resequencer.
And notice the limits. It could only make certain foods. They still needed a chef. They still had a hydroponics bay growing fresh stuff.
Right. And they also had something for waste.
Yeah, a biomatter resequencer, basically for recycling waste. You could see it as a very, very early, limited kind of matter manipulation. Less creation, more like a super advanced food processor, just rearranging proteins that were already there.
Okay, so let's jump forward to TNG. Now we've got this device that seems like it can make almost any inanimate object. How does the technobabble explanation work?
So the core concept is that the replicator grabs subatomic particles, the basic building blocks of everything.
Neutrons, electrons, that sort of thing.
Exactly. It grabs those and rearranges them to form specific molecules. Then it assembles those molecules into whatever object you want based on a pattern stored in the computer.
Like a molecular blueprint.
Precisely. One source explained it like this. For, say, a pork chop, the replicator forms atoms of carbon, hydrogen, nitrogen, and so on. Then it builds amino acids, proteins, cells, and arranges all that into the shape and structure of a pork chop.
It sounds a lot like their transporter technology, just maybe on a smaller scale.
Yeah.
Taking things apart and putting them back together differently.
That's a really good analogy. The process is described as converting bulk matter, could be anything, stored material, waste into energy, and then reforming that energy back into matter according to the pattern.
Similar to the transporter, like you said.
Very similar principle, yeah. Just focused on creating objects rather than moving people or things.
But there's a key difference in how they store the information, right? Compared to transporters.
Yes, that's crucial. Transporters supposedly work at the quantum level. They capture and recreate the exact quantum state of every single particle.
Which sounds incredibly complex.
It is. And if replicators tried to store that level of quantum detail for every possible object, well, the data storage needed would be just astronomical. Probably impossible.
So what's the in-universe workaround?
The explanation is that replicators store patterns at the molecular level instead. It saves a massive amount of data.
Ah, so it's like saving a lower resolution image.
Kind of, yeah. You lose that super fine-grained quantum detail. And that's the justification for why they can't replicate living things. You need that quantum precision for life. It's a fundamental trade-off.
Which leads nicely into the limitations. Even these amazing devices can't make everything, can they?
Nope. The big no-nos are antimatter, dilithium crystals. their warp core fuel.
Can't just replicate your fuel source. That'd be too easy.
Exactly. Also, latinum, which is their weird gold-pressed currency, and, as we just mentioned, living organisms.
And the reason for not making living things is that lower resolution, that molecular level pattern.
That's the common explanation, yeah. The replicator tech is basically a less precise version of the transporter tech. It's just not capable of the complexity needed for life.
Makes sense. What about quality? I seem to remember characters sometimes complaining about replicated food tasting off.
You're right. The sources mention that because it's working at the molecular level, small read-write errors can happen, like single-bit errors in the pattern.
So tiny imperfections.
Usually too small for us to notice consciously, but maybe detectable by sophisticated sensors, or perhaps by someone with a very refined palate. That's the in-universe reason why some people think replicated food just isn't quite as good as the real thing.
That's a neat detail, like a high-quality digital copy versus the original analog source, maybe?
Something like that. And these tiny errors, theoretically, could even be dangerous.
How so?
Well, a tiny molecular change could potentially make a normally safe substance toxic. Or it could even create dangerous viruses or bacteria from harmless ones if the pattern gets corrupted in just the wrong way. So there are potential risks.
Okay, so even with limits and potential flaws, replicators are obviously central to life in the 24th century. What are their main day-to-day uses?
Oh, huge range. Primarily food and water on ships and stations. That basically eliminates the need for carrying massive amounts of provisions.
Though they still keep emergency rations, right? Just in case.
Prudent Starfleet planning, yeah. Always have a backup. And apparently on Deep Space Nine, they even use them for breathable air breaking down CO2.
Wow, so it's part of the life support system too. What else?
Spare parts are a big one. Need a new component for the warp drive. Replicate it. Need a new uniform because yours got ripped fighting aliens.
Replicate it.
Exactly. Everyday items, too. Toys, tools, souvenirs, even stuff for the holodeck programs.
And presumably with safety locks, so you can't just replicate a phaser anytime you want.
Oh, absolutely. Safety protocols are key. No unauthorized weapons, poisons, dangerous substances.
And the recycling function seemed really useful, too. Just toss your dirty plate into the slot.
Right. They can convert matter back into energy, break it down into subatomic bits again. That energy gets stored or used for the next replication. So dirty dishes, old clothes, unwanted items, just recycle them. Very efficient.
Okay, here's a question I always had watching the shows. If they can make anything, why not just replicate entire starships?
Yeah, that's a common question. And the answer, according to the production teams, is basically drama.
Ah, storytelling reasons.
Pretty much. If you could just print out a new fleet whenever you needed one, it would kind of lower the stakes in conflicts, wouldn't it? No more thrilling shipyard construction scenes.
True. But didn't Deep Space Nine have something bigger? Industrial replicators?
Yes, they did introduce that. Not for whole ships, but for making large components very quickly. Whole sections, parts for shuttlecraft, even prefabricated structures for disaster relief.
So they could mass produce the building blocks, speeding things up significantly.
Exactly. Large-scale component replication, not whole ship creation.
And maybe the most profound impact. This technology basically underpins their entire economy, right?
Absolutely fundamental. By making material scarcity almost a non-issue for basic needs, replicators are a cornerstone of that moneyless post-scarcity human society in Star Trek. If you can make what you need, traditional money becomes much less important.
That's a huge concept.
Yeah.
Finally, before we move to the real world, let's touch on Voyager. They were stuck far from home. Replicators must have been critical.
Incredibly important, and also a source of conflict. The tech was mostly unknown in the Delta Quadrant. Species like the Kazan were desperate to get their hands on it.
And Captain Janeway refused to share it.
Right. Fear of misuse, violating the Prime Directive, giving such powerful tech to species potentially not ready for it.
Plus, their own use was limited, wasn't it? Energy constraints.
Yes, big time. On that long journey home, energy was precious. So replicator use had to be strictly rationed. They had replicator rations.
It became like currency on the ship.
Exactly. It became a de facto currency among the crew. And it's why Neelix and his galley skills, using the hydroponics bay for fresh food, were so valuable. It saved rations and boosted morale.
Okay, so that's the amazing fictional tech. Fascinating stuff. Now, let's pivot. How does this compare to what we can actually do, or what's emerging here in the real world?
All right, well, the closest real-world idea to that kind of molecular manipulation is probably in nanotechnology and molecular assemblers.
Tiny machines building things atom by atom.
That's the dream. And there's been some progress. Back in 2020, there was a report about a rudimentary synthetic molecular assembler.
Rudimentary. Okay. What could it do?
It could produce polymers, long-chain molecules. What was really interesting was that these little building blocks could first make copies of themselves.
Self-replication.
A basic form of it, yeah. They'd reproduce, and then once they reached a certain concentration, they'd switch over to building these other polymer structures. It's seen as a potential new way to design functional systems at the molecular level.
So controlling how molecules come together, maybe even getting them to build themselves first. That feels like a step. What else is happening?
Building on that idea of controlling molecules, there's automated chemical synthesis, making specific molecules on demand.
Like a chemistry robot.
Sort of. In 2015, Martin Burke and his team developed a machine that could automatically synthesize a whole range of small organic molecules. You basically tell it what you want.
Push a button, almost.
Yeah. That was the idea. It used modular building blocks, kind of like chemical Lego, and could piece them together. They made, I think, 14 different classes of molecules, some quite complex.
What's the application for something like that?
Huge potential. Speeding up drug discovery, creating new materials for electronics or solar cells, making research chemicals much faster.
And they had some clever purification system, too.
Yeah, a catch-and-release system. The building blocks they used could also act as tags to hold the growing molecule while they washed away unwanted byproducts after each step. Very neat.
Okay, so we're getting better at building specific small molecules. What about bigger structures or things that can change their form? Programmable matter.
Right, programmable matter. The idea there is a substance that can change its physical properties, shape, color, maybe stiffness, based on instructions.
So it's like the replicator assembling matter based on a pattern, but maybe at a larger scale, changing the form of something that already exists.
Exactly. It shares that concept of matter conforming to programmed information. Imagine materials that could reshape themselves on command. The tech is still very early, but the concept is definitely related.
And what about machines building copies of themselves? That always sounds very sci-fi.
That touches on theoretical work on self-replicating systems. Researchers are modeling how mechanical systems, not just biological ones, could reproduce.
Like robots building robots.
Kind of, yeah. They break down self-replication into functions like finding parts, copying instructions, assembling a new unit. It's mostly been done in computer simulations so far.
So the theory is being explored.
Yes. And you can imagine if you combine these ideas, automated molecular assembly, with some form of self-replication, well, the possibilities get really interesting, though still very far off.
Okay, let's bring it back to something more tangible. Maybe the most direct comparison people think of is 3D printing, especially for food.
Absolutely. 3D food printing is probably the most recognizable analog to the Star Trek food synthesizer or replicator.
And NASA's even looking into it, right? Space pizza.
Yeah, NASA's invested in it for long space missions. The idea of printing customized meals, maybe even pizza, for astronauts is definitely being explored.
Sounds good to me. But it's fundamentally different from a replicator, isn't it?
Oh, completely different mechanism. 3D printers, food or otherwise, work by adding material layer by layer. They need pre-existing ingredients, inks, powders, filaments, food pastes.
They're not creating matter from energy.
Exactly. They're just shaping material that's already there. A Star Trek replicator, theoretically, is taking energy or basic subatomic particles and building matter almost from scratch based on information. A huge difference.
And 3D printing materials are still somewhat limited, too.
Yeah, mostly plastics, some metals, ceramics, concrete. Food is tricky. It's not the universal material capability of a fictional replicator.
Okay, now for maybe the out there, but scientifically grounded idea, making matter from light. You mentioned the Bright-Wheeler process.
Right. This goes way back to the 1930s. Bright and Wheeler theorized you could collide two photons, particles of light, with enough energy and create an electron and a positron pair.
Matter and antimatter, created purely from light energy.
Exactly. MC art in action. It's seen as the simplest way light could transform directly into matter.
Wow. Has that actually been done? Seen in an experiment?
The pure two-photon version is incredibly hard to do. You need incredibly powerful focused gamma ray beams, which are tough to make.
So technically challenging.
Very. But a related process, the multi-photon Bright-Wheeler process, has been observed. That's where a single high-energy photon interacts with a strong electromagnetic field, like from a powerful laser, and still creates an electron-positron pair. That was done at SLAC back in 1997.
So we have seen light turn into matter in the lab.
In that specific way, yes. It's a proof of concept, even if it's just creating fundamental particles. And scientists are still trying to design experiments to see the pure two-photon version. There was a proposal in 2014 using intense lasers and a gold target.
That feels fundamentally closer to the energy to matter idea, even if it's just electrons and positrons right now.
It's theoretically very significant, yes.
Okay, so we've got these molecular assemblers, automated synthesis, 3D printing, even matter from light experiments. But let's face it, there's still a huge gap. What are the biggest hurdles, the fundamental barriers between this and a real Star Trek replicator?
The absolute biggest one is that core difference. Our tech rearranges existing matter. Fictional replicators fundamentally convert energy into matter.
And EC Hot tells that takes a lot of energy.
An unbelievable amount of energy. To create just 1 gram of matter, like the sugar cube's worth, you need the energy equivalent of a small tactical nuclear weapon.
Wow, okay. That puts it in perspective. The power requirements are just staggering.
Monumental. That direct energy to matter conversion on demand is the key piece of magic we absolutely cannot do right now. We're just rearranging atoms and molecules that already exist.
And besides the energy, there's complexity and scale, right?
Yeah, definitely. What we can assemble now, molecule by molecule, is incredibly simple compared to, say, a cup of coffee, let alone a complex device. And replicating biology, with all its quantum intricacy, that's orders of magnitude harder still.
I also saw the U.S. military is using the name replicator for something. Is that related?
Yeah, the DoD's Replicator Initiative. It's an interesting name choice, but it's actually about something different.
Not matter conversion?
No, not at all. It's about mass-producing autonomous systems, like thousands of drones, very quickly. It's about manufacturing scale and speed for military hardware.
So replicating capability, not replicating matter itself.
Exactly. Different concept, same name. Though you could argue rapid production of complex systems is its own kind of replication.
So pulling it all together then, how close are we, really?
Honestly, not very close to the Star Trek ideal. We've got automated machines making small molecules. We've seen simple polymers assemble themselves. We can 3D print food from pastes. We have theories about self-replication. We've even turned light into particles. But putting it all together to create complex objects on demand from basic energy or particles, that's still firmly in the realm of science fiction for the foreseeable future.
It's still such a fascinating place where science fiction meets real science, though.
Yeah.
Seeing these, like, seeds of ideas starting to sprout.
Absolutely. We've unpacked the cool ideas behind the fictional tech, seen the genuine, exciting progress in related fields like nanotech and synthesis.
And we've also hit those hard walls. The energy, the complexity, the huge challenges still ahead for anything like true matter replication.
It really makes you think, though. Even if we only achieve limited versions of this tech, what could that do? How could society change if we could easily assemble complex molecules or print intricate structures on demand?
Yeah, what happens when today's limitations get chipped away by discoveries we can't even predict yet? It's definitely something to ponder. Exciting, maybe a bit scary too.
It really is. It pushes us to think about resources, manufacturing, maybe even what value means. Science fiction like Star Trek gives us these incredible goals, and the journey towards them, even if we never fully arrive, drives so much real innovation.
Well, this has been a truly fascinating deep dive into replicators, fiction, and fact. If you enjoyed this journey into where science meets imagination, please do like and subscribe to Teolumen Insights. We'll have more deep dives coming your way.
Thanks for joining us and exploring this with us.
Until next time, this is Teolumen Insights.